So I think everybody seems ready. They are sitting down. And if you want, you can go ahead.
Thank you. So we speak about, Amalia told me about some codes that you don't have. We will speak, we'll busy about this later. Just I would like to go on because we have no so much time. So if I go back to the snap, all right, for the difference between VH and VV. And as you can see here on this image, lines are horizontal and columns are vertical. So this image is in image geometry. It is not map projected. So we are going to project this image and also to calibrate it. The calibration corresponds to go from the digital number to the physical measurements, which is the radar reflectivity or radar reflectance, and the name is radar backscattering coefficient. To do so, I have prepared a graph. So what is a graph? A graph, with a snap, you can do a lot of processing and you can make a processing chain. A processing chain, the name is graph. And so you can access to the graph by clicking on this button. Do you see it?
You need to share the screen.
The screen is not shared. This is a nice remark, a nice comment. Wait a minute, I'm here, share screen. All right, now you should see it. Yes? It's okay? Do you see my screen?
Yes.
Yes, all right. So in order to load, to access to Graph Builder, you click on this icon. Do you get it? Do you see it on my screen? It's okay?
Yes. Yes.
So you just open it and you can, we are going to load a graph that I build and that is dedicated to the calibration and to the ortho rectification of Sentinel-1 data. So load graph, then you go to French Guiana, codes, snap, and then you take graph S1 subset Cayenne orthocal. It's okay? Okay, and you should see this graph. It's okay for everybody?
No. No.
Tell me, what is the point? Do you have the graph builder? In the graph builder, you just click on File. Amalia, tell me before it begins a riot. Huh? Just tell me the problems and I can help you. But now here I don't know what happens.
Can you repeat, please, again?
Alors, I repeat. I close everything and I repeat. I want to load a processing chain which is called a graph in Snap. So to open the graph builder, the graph, it's this button. Does everybody see it? It's okay?
Yes, okay.
For other people, you can go to Tools and Graph Builder here. It's the same. Everybody got the Graph Builder open like this? Yes?
Yes, everybody, yes.
All right. Now, File, Load Graph. Okay? It's okay?
It seems okay, yeah.
All right. And now we go to C, French Guiana, Codes, Snap, and you load graph S1 subset Cayenne orthocal.xml. It's okay?
Okay.
Okay. And so you see all the graph here. So I just went to on internet and I Google calibrate and orthorectify snap sentinel, and I got what you have a lot of tutorial everywhere to explain you how you do it. So you read the data, you apply an orbit file in order to get a more precise position of the satellite. You remove the thermal noise of the sensor. Then I don't want to use it on the whole scene because I'm just interested in a subset. If you click here on the subset tab, you see it there. Here you have in red all the scene, and in yellow the little subset that is centered on Cayenne here that we see here. So it's okay. I just take the subset. I apply the calibration. The output, if you see on the tab, the output will be sigma 0. I hope I will have a little time to do it. Then the same subset again to have the image vertical and horizontal. If not, it's a little skinned. And then I write it somewhere. It's okay? Is it okay?
No.
So thank you for telling me now, but could you please tell me a little more?
Excuse me, in the right tab, do you need to enter the directory of...
Not yet, later.
Okay.
Later. So the woman who told me no, where is she in the process?
Everybody is okay? Yeah? You have a question?
The woman who told me no, does she get this graph loaded? The woman disappeared.
Yes? Yeah.
Do you hear me?
Yes, we...
I put also, did you, in the chat, I put 2 roadmap Riga 22.pdf, one roadmap snap, the other roadmap is without snap. Do you see it in the chat?
Yes.
So download both, and what we are doing to do now is just the beginning of roadmap snap Riga 22. All right, it is this one. And we are just doing this here. open the graph builder. It's on the bottom of the third page. Can people who doesn't have loaded this graph S1 subset Cayenne orthocal.xml can tell me that it doesn't, and we do it together? Or everybody get it? Yes?
Yes.
So we are going to apply this processing chain to all these 4 files, these 4 Sentinel-1B files. All right? And to do so, we go back to Snap, and now we are going to click on this, just the icon just near the last one. The name is batch processing. All right? Or if you prefer, you go to Tools, and here, batch processing. Is it okay? You have this, which is open, batch processing. And now, what processing? The processing that the one of we just opened here in Graph Builder. We opened it in order to be able to see what is this processing. So now, File, load graph, and again, I load exactly the same. S1 subset Cayenne orthocal.xml. File, load graph, and this one. Is it okay?
Yeah, it's okay.
Super, super. So now, input-output parameters, you click, oh, no, excuse me. We are going to open in Snap the 4 products. All right, in Snap, there is just one product that we have opened. Before, now we are going the 3 other products by selecting them in the file manager and drag and drop into Snap. Is it okay?
Yes.
Everybody must have only these 4 S1B products open in Snap. The products open this morning has to be closed before. If you want, if they are open, you go to close all products. And then here you go again to S1 zip, and you drag and drop the 4 S1B acquisition into Snap. Is it okay? Yes?
Yeah.
Yeah? All right. Now, if you click on this little button now, if you click on this button in the batch processing window, you will add all the opened files in Snap. Up, if I click, I have the 4 files that appear in input-output parameters tabs of my batch processing window. Is it okay?
Yeah.
Yeah? All right.
Yeah.
Apply your bat file, nothing to say. Thermal noise, nothing to say. Subset, nothing to say. You see, it's okay. Calibration, nothing to say. Terrain correction, a lot to say. So just I open more my. First here, I will change. I don't want that Snap automatically download the DEM. How the rectification is made. As we know the position of the sensor when he has acquired the image, you simulate the image you would get if with a digital elevation model. And then with this, you make a correlation of the image due to relief distortion. You can make a correlation and locate very precisely the image on the digital elevation model. So we need a DEM. In general, we use the shuttle radar topographic mission DEM that has been acquired with the shuttle, I think in '84 maybe. And by default, it Snap auto-download it, but I did it before. So you just click here on external DEM. Is it okay? Yes?
Yes.
Then here, external DEM, you go to French Guiana, data, and DEM, and you click on SRTM 1 second arc Cayenne.tif. All right, in French Guiana, data DEM. Do you get it?
Yes.
So you make OK. Then here, map projection. The map projection will be the universal transverse Mercator that is fitted to the French Guiana geography. So you click on map projection here. All right. And now you click on predefined CRS. CRS means coordinate reference system. It is the map, the map projection. Is it okay for everybody? You have clicked on it? Once you have clicked on it, you select here. And here you click on UTM, WGS, oh no, UTM 22 North, and you don't get it. So UTM, wait a minute, no, you click on 32, 6, wait a minute. All right. So here you click on 32, 6, 22. Is it okay?
Yes.
And then you click on this one. This is the ellipsoid that is used in the WGS84, and it is the Universal Transfer Mercator, Zone 22 North. All right? Then you click on OK, and it's done. You have the good one here, which appears, WGS84 UTM Zone 22 North. All right? Is it okay?
I think it's okay, yes.
All right, super. Thank you, Amalia. Then just in right, you just have to select the good repertory, the good folder. So you go to French Guiana. I have to go there. And go to Snap. Oh no, just just go to Snap. And orthocal. Wait a minute, I'm sorry.
I'll ask him to repeat. Pierre, can you repeat?
Yes, of course. So just here, you have to change in the tab right, you have to change the output folder. So here, you go in the tab right, and then in directory here, you click on the 3 points, and you go to French Guiana. Then data, S1, and you can add here orthocal. All right, here you can add ortho for ortho rectification and cal for calibration. And avoid the space. Like this. Is it okay?
Yes.
Then select. And so all the ortho-rectified calibrated data will be put in this repertory. And then you can click on run. All right?
People are copying.
What happened? Is it okay?
Is it running well for everybody? Problems? Problems anywhere? No? Sorry? Oh, okay. Are you having a problem? Okay. Any problems here? You have problems? Okay.
I think it's not.
It's processing. It's processing.
Okay, so everything's happening.
Yeah.
It's just doesn't.
You have the same, right?
No, I have not right.
What is the error?
Okay.
Oh, okay. Yeah. I'm good.
You have no what? You have no right, exactly. Okay, so I see that now this little bar appears, so I think you're fine. And you'd have no. Can I? Oh, you have no right. Let's close this one. Add it.
Is it okay?
There are some minor problems here and there.
What kind of minor problem?
Well, in one of the graphs, right is not appearing in the tabs, so I'm trying to solve that. Um, oh, of course I know. Sorry, I was. Wait, this is because input output parameters. Can you just tell me? So you created this graph, and then to do this, you went to batch processing here, and you opened this tool, right?
Yes.
Then you load the graph. Okay, so I think then we do it from here. One second. Can I just check? It worked for you? Yeah. Can I ask this? The path you modified it from here, right? Not from the batch processing. Okay, okay. Yes. Okay. Yes, yes. Double checking that this is correct. You don't need to add orthocal too. He was doing that before because he already has a folder called orthocal, so he didn't want to overwrite it. But you don't have one that does Sentinel-1 snap. No, actually, no snap. You have it here. That is true. All right, but it is empty. Pierre-Louis? Pierre-Louis? Can you hear me? Pierre-Louis? See, 1 second. I come to you. Pierre-Louis? Oh, he left us. He left us. Okay, never mind. Well, then I suggest that you do like these two, and then you just continue with that. So I think you can do run. But because I wasn't here until 10 minutes ago, I don't know why you have this open. Because
I can to start one more time.
maybe when Pierre-Louis is back, did you do it like this as well?
Sorry, Amalia, I'm here. I'm here.
Okay. Oh, okay. Yeah, so I'm going to ask him, Pierre-Louis, so I am a bit confused because I had to step out of the room for a second. So you first make the graph, and then in the right tab, you adjust the directory, right? And then people also open the batch processing, and they run the graph from there.
So
Is that right?
the graph builder is not important. It's just for them to see what they do. But it's not open. It's not important. The most important is the batch processing. Then you load the graph.
Okay.
You
So
load
did you load the graph? Yes, you did, because it was this one, right?
You load this one.
It's already loaded. Okay, and then they run it. So now you
All
just
right.
run. Let's have a look. What is it? You're getting an error.
Yeah.
Okay, and some people are getting an error called GC overhead limit exceeded. I'm gonna check if somebody else there also has that error. Did you?
What is the error?
So the error says GC overhead limit exceeded.
She has different.
Okay. Something about also Java heap space. It may have to do with the computers, the local computers.
So what is
I'm gonna share your screen. I'm gonna
RAM that is that are on these computers?
I'm sorry, what? The
The
RAM?
RAM
16.
16. It should be work. It should work. It should work. I don't know that. And so this is Snap is wonderful because it's an interactive, an interface very well done. But this is the big problem when you make processing. Sometimes you have error and you cannot do anything. You don't know where does this error come from. Sometimes it is because of the RAM. Sometimes I don't know. So I see that you have people who are on a blog about Snap, and they can ask questions and have answers. But this is the reason why I don't like so much Snap. For educational purpose, it's wonderful. When you want to make serious processing, you can have errors. Most of errors I saw came from the RAM. So, for example, the people who gets the error, does he have other things open on the computer?
Well, nothing exceptional besides the internet browser, Zoom,
Yes, I don't know.
and the PDF. No, it's only happening to some of them. Are the outputs in a backup folder?
So, we have less than 1 hour, and I have a lot to do with you. So, I continue a little with theory, if you agree.
But Pierre, one question: the outputs that they were meant to produce, did you perhaps have a backup folder?
Yes. I have a backup folder. I have it here.
Can I? Yes. Is it the rescue? Oh, I'm blocked.
I have.
Sentinel 1 or Sentinel 2? Sentinel 2. No, this is not. Oh, this is the results. Where's Okan? I'm gonna ask him. Is it in Rescue Sentinel 1 Orthocal P47?
Yes, you have it. Wonderful.
Yes.
Whoa. Wait a minute.
Okay,
I
this is
don't
it.
recall. Ah. Yes, in Rescue, Sentinel 1, Snap. What do you get?
Orthocal. Orthocal P47.
Eh ben, super, you get it. You get it. So, how do you do this? Now, yes. Then you open and you just click on the four DIM files and you drag and drop.
But are you in Snap or in Orthocal?
Here I am in Orthocal.
I think you're in Snap.
Yes, but you have Orthocal. I didn't.
Okay.
Wait a minute, I do it.
Because I saw an Orthocal folder when you...
Yes, it's not the same. Wait a minute, up.
Yeah, that's fine. So this is because he's now going to process what you already have here saved. See?
I'm in Orthocal here, and you should get this one.
Oh, I see what you mean now.
And now if you click on this 4.dim file, you drag and drop it in Snap and you get it.
Not exactly.
No.
Not exactly. I'm going to share with your screen.
Oh,
I'm going to share the screen so that you see, you can screen share while other participant is sharing. Oh, okay. I'm going to, now he stopped sharing, so. Are we sharing? Okay. So Pierre-Louis, now you would see the screen of a participant who got an error, okay?
Wait a minute.
Okay.
But I closed the error tabs.
No worries, that's fine. I just want to show
No.
you.
Oh, yes, it's not a good one.
You can see now?
Yes, I see. S1.
So rescue, then S1, and then
Snap. Go to Snap.
Snap.
All right. And now you have you click on the three last files.
These three ones.
And also the first one over.
This one.
Yes, thank you.
Okay. And we will open them on Snap.
Yes.
Okay. So if we can close already the batch processing and the graph, right?
Yes.
Okay. So if you don't mind, I'm going to go ahead and close this. I close this and this for clarity. I close this. And do we close everything that is open in Snap?
You can close the four first. The four first
ones. Okay. So I'm going to say close product. Close product. Close. And close. And then we can.
Press control.
Oh, but they are already open. They are already open. Look at it. she gets a subset, and at the end, orbital files.
Hold on a second.
Noise rush. Yes.
So it seems that even though Snap gave an error, it's still produced.
So just to get, yes.
Oh, it is still produced it. So it means that she didn't have a real error.
But it just verify the for acquisition, both polarization to be sure. VH and VV also. Yes, okay. Okay.
I see something here.
And VH, what happens for
Well,
VH?
I'm gonna close because I don't know if it's the window or what, and I will reopen this. You
The last
see.
one couldn't process because
Yeah, exactly.
So I can run just the processing for the last one. The first three.
Okay. Do you? So Pierre-Louis, it seems that in the case of in her case, the first three ran correctly, but the last one did not.
All right.
So she could rerun the processing only for the last one.
Or she just can
Or just copy it.
From the rescue folder
Yeah.
the last file.
Okay. So you can close that one. Yeah, you can close it.
And from the rescue folder,
And it would.
The one of 2018, the last one,
this one.
with the folder associate.
Yeah.
This one. Okay.
So you can drag it, and this. So she would copy. Sorry, this one and this one to orthocal.
Yes.
Okay, so we can. Wait one second.
I already copied that inside.
Okay, and now he wants you to copy it. Copying it in orthocal.
Yes. No. Not in rescue. Not in French Guiana. Data. S1. Snap. And orthocal. Oh, you don't have.
I saved it in this one.
That's
All right.
orthocal.
Article 2.
It would be here, where we would need to overwrite.
I don't know if it's orthocal or orthocal 2.
It's orthocal too, yes, because that's what she put.
Here, do it and
Paste.
yes.
And 7, it means that this one can go, because this is the same one.
And this one.
Now there is an
Yeah,
error.
this one is new, so this one
No,
can go.
no, wait a minute. Oh, yes. I think it's not the. I made a mistake when I put it because it's not subset, etc. So I don't think it's.
Oh, okay.
I'm sorry.
So this one better not to put it here, not to mix it with the other ones.
Wait,
She could just.
Yes, it's okay. It's a good one. It's a good one, but not the same. It's another. It's okay. You can check. It's a good one.
It's a good one. What? This one?
Wait a minute. I have lost. Good. Yes.
Yeah,
okay.
it's a good one. Okay.
Yes.
Yes,
So,
you can keep it.
so
And then this one can be deleted, I
This one
presume.
you can press control, so you can delete also this one.
This one. Okay, perfect.
And
There you are.
I can. Folder new.
Oh, well, okay. It's gonna delete one of them, but not the other one. You can do it later when you close Snap.
Okay.
Okay. And now, if you want to
Need
stop sharing, yeah, you can click there. Yeah. Okay.
Thank you very much, Malia.
Nothing. I hope it helps others who had this same error. But not sure. Is it going over here?
I think she didn't save in the correct directory the files, so she's looking where they went.
So now it's blocked your computer. Is it blocked?
Wait.
The computer or the way? No. You're searching for it because you don't know where is it. Okay.
Yeah.
All right. I know where. Otherwise, everything is in rescue. So. So Pierre-Louis?
Oui.
So, yes, I think you can continue and I will help some people here.
Oh, thank you very much. So, I think we have to make choice because we have 45 minutes. And so we won't be able to process all the data. And so the practical, I think the best should be to stop the practical. You get the roadmap I send you both, either with Snap or with QGIS. It's the reason why we developed with my colleague from Office National des Forêts Internationales the tool with QGIS, because when you make some formation to non-specialists in Africa, in South America, they don't get powerful computers. And so they are very quickly stopped. And so we developed it with QGIS. So you have both roadmap, either with QGIS or with Snap. And what I think, I would like to present you a little more theory about radar. And in any case, you will practice tomorrow with my colleague, which will speak about Sentinel-1 and Sentinel-2 for forestry. So I think it would be better to present you what the theory about the radar response sensitivity, the surface parameters to which the radar is sensitive and how it is sensitive, relief effect, and some rapid statement about the filtering of the speckle. What do you think? And if we have time to continue the processing to make vegetation maps of the different type of vegetation with Sentinel-1 data, are you agree with this, or you prefer do other things? So, in any case, you have the roadmap. Do this roadmap. I will be pleased to answer to any of your questions. You don't find a button, you have an error, you don't, you can't imagine the number of errors I got. So no, don't be afraid to have errors. Errors are always stupid, and so send me an email. And I help you to proceed all these practical by your own, following the roadmap. Are you okay?
Yes, okay.
All right, so we have 40 minutes. This is just some computation, just to show you what is the radar equation. You have similar in optical data. You just have a radar equation which relates the receiving power, the receiving intensity to the emitting intensity. You emit a pulse with a given intensity. And then this pulse travels, go to the target at a r distance. G corresponds to the gain of emission and reception. It's a system constant. We don't care. Lambda is the wavelength depending on the system. R is the distance between the antenna and the Earth, and a radar is computing R because it measures the times delay between the pulse emitting and the echo that is backscattered. So this he knows R. Everything else here are some system constant, the emitting power, the emission gain, the receiving gain, and there is just one thing relating the recording power to the surface, it is the equivalent of optical reflectance. In radar, we call it the radar cross-section. All right? The radar cross-section is the cross-section that is seen by the waves of the radar. For example, you can have a very big object, but that is quite transparent for electromagnetic waves. So we will have a very small radar cross-section. Or you can have a very small object that is highly reflecting for radar waves, and he will get a big radar cross-section. So radar cross-section is in meter square, and in fact, we prefer we prefer manage the radar backscattering coefficient, which is the radar cross-section divided by the surface of a unit surface area. This radar backscattering coefficient is without any units, and this is analogous to the reflectance in optical domain. And due to really high dynamics, we reduce the radar coefficient is characterized by the very high dynamic, much higher than the dynamic of optical reflectance. And so this high dynamic is chosen to be reduced by using a logarithmic scale. And so we prefer use the radar backscattering coefficient in decibel, which is just 10 multiplied by the logarithm in basis 10 of this that you get here. And so all people who make radar knows, for example, that with Sentinel in VV over a forest, a dense forest, you have a radar backscattering coefficient of about -7 dB in VV polarization, for example, and maybe -10, 12 dB for VH polarization. We all discuss with this decibel and not natural scale. Now, what happens when electromagnetic waves interact with a natural surface? You have two cases of figure. Either you have over bare soil, and then we speak about surface scattering. The interaction occurs only at the interfaces, the interface between the upper layer, the air, and the down layer, the ground. Inside, if the ground is homogeneous, you don't have anything, you just have an interaction at the interface. We speak about surface scattering. And when you have vegetation, we speak of snow or ice, we speak about volume scattering. This corresponds to a lot of different scatterers, which each individually interact with the electromagnetic wave. In that case, we speak about volume scattering. So, in the case of surface scattering over bar soils or water surfaces, this is theory. Over a perfectly reflecting surface, totally flat, all the incoming radiation will go into the specular direction. So if you have a radar here, you don't see any backscattered echo because all the incoming wave goes in the specular reflection. If the surface is a little rougher, you will have some faces which will backscatter a little power, a small quantity of power back to the antenna, and you see a little, very small response. And if the surface is very rough, you won't have any coherent components, but you will have as many as facets that will irradiate in all the direction. And so in the backscattered direction, you will have a very high backscatter intensity. Of course, this, so the surface, you just measure every centimeter, for example, the elevation. Then you can measure the average, the mean, and the standard deviation around this average. And so the roughness corresponds to this standard deviation. And this, the roughness depends of the standard deviation with respect to the wavelength. Of course, if you have 20 centimeters of wavelength, 1 centimeter of standard deviation won't be very rough. It will be totally flat, while totally smooth. While if you look at the same with a 3 centimeter wavelength, it will be really rough. So the roughness depends on the surface, of course, but also with regard to the wavelength. So now here you just look at the radar response with respect to the incidence angle of the observation. So of course, when you see on the nadir, when you look at of the nadir, you will have a lot of energy which goes back when you are on a smooth surface. And then when you look at with higher incidence angle, if the surface is smooth, everything goes on the specular direction. And so you have a decreasing of the signal very quickly with the incidence angle. If the surface is very rough, you don't have any backscattering preferred direction. In any direction, you will have the same power quantity which will be backscattered. What are these two parallel curves? This just corresponds to a dry surface here and a wet surface one. So the angular shape depends on the roughness, and the absolute level depends on the moisture of the soil. So it's the reason why, for example, it's very easy to detect most of time. Sometimes it's not the case, but if you have oil spill in the water and the oil is on the surface, so the oil will be totally smooth, and so all the incoming wave will go to the specular direction, while beside the oil spill, you will have roughness due to wind, and so you will see bright returns. And so it's the reason why you see very well here this oil spill backside a ship. Here, typhoon seen in optical with MERIS, in radar with ASAR NVSAT, ASAR sensor on board NVSAT. You can see the same features, but with optical data, you just see the wind, the clouds. The clouds accompanying the typhoon. Here, you don't see the clouds because with 6 centimeters of wavelength, you don't see the clouds. But what you see is the roughness of the surface of the ocean. And in the eye of the cyclone, you don't have wind. And so the surface is totally smooth. All the signal goes to the specular direction. You have a very low return, backscattered return. While everything over here, you see the roughness state of the sea, which is closely linked to the shape of the depression of the typhoon. Here, the same, the same region seen by GRS sensor, 25 centimeters of wavelength, ERS sensor, 6 centimeters. You can see that here the surface, ocean surface is very low because for 25 centimeters, it's rather smooth, while at the same time, the same surface state is quite rough for 6 centimeters and returns quite a lot of energy. Here, over surface, so this is in Sahel when you don't have any vegetation. It's during the dry season, it's just sand. And you see this. What is this? It's, what's the name? Dill? Spill? No, what's the name? Wait a minute. A dwell? A well. It is a well. So it is a well, and you have a lot of cattle who comes. The land is wet, and so the cattle produce a huge roughness for 6 centimeters wavelength, and it's the reason why this is bright and everything is darker surrounding it. Here you can see a geological map, just because the different type of rocks corresponds to different type of orientation here, and also roughness there. It's the reason why, for example, here corresponds to that, C corresponds to this, and limestone here corresponds to this here. Flooded is maybe very easy to detect, to monitor flooded areas with radar. Flooded areas occur when it's raining. So with optical data, you are really embarrassed. So if you take radar, it's nice because you don't see the clouds and you can see the flooded areas. But for this, you need flooded water totally calm to be really dark. If you have wind and the flooded water is rough, you won't be able to see it. But if you are interested in it, of course, look at what happens with the radar. You can extract it easily. The penetration effect, the longer the wave length, the deeper it can penetrate if the media is dry. So, for example, here, it's a desert in Algeria with optics. So with optics, you just see the sandy veil here. And the same area with ERS, 6 centimeters of wavelength, you can see the buried structures, geological structures under the sand. This is because the sand is really dry and there is not so much sand over the buried geological features. The same here. This was a shuttle radar mission, and they showed this is an optical image in yellow of Arizona desert, and with a L-band you can penetrate and see under the sand veil. I don't speak about this, I don't have time. Over vegetation. Over vegetation, it's an inhomogeneous medium, and the wave interacts with all the individual scatterers. What is a scatterer? A scatterer is the smaller object that interacts with the wave. And in general, a scatterer has the same size or larger than the wavelength. So for example, yes. Wait a minute. What happens when you are looking at a forest with X-band, 2 centimeters? The scatterers corresponding to X-band are objects of wide 2 centimeters or larger. In other words, it corresponds to all the leaves and little stems. And so the incoming wave, the incident wave, interacts with all these scatterers and won't penetrate too much because lose its intensity very quickly because it interacts with all the small objects of the top of the canopy. So with 2 centimeter wavelengths over a forest, you just see maybe 1 meter of the top of the canopy, I think less. With 6 centimeter, you see not the smallest, what's the name? Leaves. I begin to be tired. So with 6 centimeters, you don't see the smallest leaves, but you will see bigger one, stems, and so you will interact less with so many small scatterers that as in expand, and you will penetrate a little more. With 25 centimeters, you won't see the leaves anymore. You will see the bigger branches, and so you penetrate deeper. And so the penetration depth is proportional to the wavelength and, of course, to the density of the vegetation cover. So this is an experimental estimation of the penetration depth, which depends on the density. This is the imaginary part of the dielectric constant of the medium of the layer and the wavelength. And so the larger the wavelength, the deeper the penetration. And it's the reason why there will be the biomass satellite, the biomass sensor, which will be launched next year, and that will use for the first time in the history P-band radar, because its objective is to estimate the high biomass values which are contained in the tropical forests, which represent about 80% of the global biomass over the world. So you have, when you have volume scattering, you have penetration, which depends on the density of the media and the wavelength. Just here. Yes, it works. So this is the same area in a tropical forest, seen by L band, P band, and C band. So when you look at, you can see that with P band, you have a very contrasted, high contrasted image, because the vegetation layer is highly penetrated by P band, and so you see a lot of differences, a lot of because it's not uniform forest. While for C band, it's quite homogeneous because C band doesn't penetrate a lot and don't see the differences between the structure of the forest. And L band, it's an intermediate state. The same French Polynesia island I showed you, but before it was just one wavelength and 3 different polarization, and now it's one polarization, VV for all, and 3 different frequencies, wavelength, 6 centimeters, 25, and 70 centimeters. And you can see also that these difference of penetration depth allow to discriminate well between different forest types. All right, I told you this. This is the response of the backscattering coefficient in function of the biomass. And you can see that whatever the 3 polarization, it increased at the beginning and then reach a saturation level. For example, here, after 300 tons per hectare, the radar cannot estimate between 500 and 300 tons per hectare, and biomass forests are the biomass levels that you encounter in biomass forests are around 400, 500 for the most highest values. So with C-band, you stop at 20, you saturate at 20 tons per hectare of biomass, L-band 40 tons per hectare, P-band 100 tons per hectare. This is a very old paper, but now maybe with C-band we reach 50 tons per hectare, L-band 100, 120 tons per hectare, and with P-band, I won't have time, but we can can estimate up to 400 tons per hectare of biomass, and this is quite challenging because it will be the first time that we will have knowledge of the distribution of the biomass at the global scale. When you have a radar over vegetation, you always get three different backscattering mechanisms. One comes from the surface beneath under the vegetation. One comes from the volume scattering on the canopy, and the last one comes from the double bond effect that occurs with the corner reflectors. And when you have when you are looking at vegetation with radar, you have always these three contributions which are merging together. Sometimes one is totally negligible, other time is not so negligible, and so you have always to deal with these three interactions, and the reason why we use models to better understand the radar response over vegetation surfaces. So the sensibility of radar observation, it's sensitive to biomass, structure and moisture of vegetation, structure above all with polarization, and moisture because radar is sensitive to moisture, and to the roughness and moisture of soils. So with radar, you get access to key variables. So first, vegetation discrimination, if you want to, it was the purpose of the practical that we won't have time, I'm sorry, to complete. Also, an estimation of the biomass. And this is a direct link. Because of the penetration depth of the radar is sensitive to biomass. Sometimes you can find some studies that are published which estimate biomass with optical data. It is possible, but this is indirect correlation. Optical data is not directly sensitive to biomass. It is sensitive to photosynthetic active pigments of the canopy and their density, and with indirect correlation on some sites, some other specific sites, it can be correlated to biomass, but it's not a direct correlation as radar. You can have also, you are sensitive to vegetation phenology, and this is one of big asset of Sentinel-1 and the high temporal repetitivity that it allows. We can also, as it is sensitive to moisture, it can be, and we are working on it now, to monitor the stress of the crop fields. Because if we can have an alarm as soon as possible is better, and on soil moisture. I pass this. I pass all of this. Just, I'm sorry. Yes, this was for forest monitoring, but I think my colleague tomorrow will speak much longer about this, so it's okay. Two things. Few words on the effect of the relief. Do you have some questions? It's okay?
There is one question.
Yeah, I have a specific question on soil moisture and roughness. Do I understand correctly that on Wednesday we'll be talking more about this, how to get specific parameters for these things in agriculture section?
Yes, I don't know. I don't know if it's planned on Wednesday. Yes.
Okay, thank you.
Yes, it's Wednesday.
I don't know.
Yes, it seems so.
So yes, it's of course it's a particular relevant topic, huh? And but all the deal is to deconvolve the moisture effect and the roughness effect in the radar response. But I hope you will have a lot of details on Wednesday. Yes. Is it okay?
Yes, thank you.
Do you want other questions? Do you have other questions? So just some words about relief effects. In with just all right with optical data, the acquisition is always made close to the nadir. So relief effects are sometimes visible if the sun is too low, but in general, they are not as sensitive as relief as the radar. And so radar is very sensitive because it looks at, it is a side-looking system with high incidence angles. And so, for example, here you see that all the face oriented toward the radar are really bright. And so here you can see when the radar is here, this is the radar natural geometry, and these segments has all the same length, but are not oriented in the same way. So you see that the faces toward the radar are contracted, while the faces backward the radar are shrinking. And so you have distortion, and this is a main limitation of the radar. And for example, if you are interested in this, in a topic, you want to look at radar, in a first approach, I would suggest you to use a mask and don't analyze the surface with slopes higher than 20 degrees. We do it most of the time. Radar over relief is very difficult to use, and over flat terrain, it's much better. So, of course, if you look at with the higher incidence angle, you even won't see the backward face, and it will be in shadow. All right, it's okay. I won't speak about this. I don't have time. this is just a processus of orthorectification. This is the image geometry. This is the after orthorectification, and you see that the radar is here, was looking there. So this slope, which is oriented toward the radar, is totally contracted. And when you orthorectified, you shrink this this slope, and you get this. And so, for example, it's very complicated to study the answer over the response of the radar over this slope facing the radar. This is a zoom, and so you can do anything with slopes too high, over 20 degrees. Then, okay, all right, and just few words, but it will be very quick. Few words about the speckle. The speckle, what is it? When you look at the image you have processed, orthorectified, and calibrate, when you look at full resolution, not so good, because it's black and white. Of course, you have just one channel, just a VV or VH channel, and you see that you have a lot of noise. This noise comes from the physics of the radar when you use coherent wave. When you use coherent wave, depending just when you have just two objects, you use a coherent wave. You just use two objects, and each object is identical, and so has the same amplitude, but the phase depends on the one-way back. The phase depends on the distance between the antenna and the scatterer. And you can say, but I don't care, this is just 10 centimeters, here it's 1,000 kilometers, I don't care. No, it's relative to the wavelength. So if the wavelength is 6 centimeters, you can see that if you have here a difference of just 3 centimeters, both contribution will be added, will be in phase. If it corresponds to 1.5 centimeters, you will be out of phase. And when you have coherent wave, when you make the summation, the phase is important because you have here both waves here in phase. So when you add both, you have twice amplitude, and when here they are out of phase, the one is the opposite of the other one always, and you have always 0. And so this just depends on the distance between both scatterers. This is when you have just 2 scatterers, but if you have one, for example, when you have 25 meters of spatial resolution and you are looking grass field, you have thousands of little grass, and these are distributed randomly, and so you will have a lot of different waves which combine randomly. And so this is a simulation. Suppose that you have a perfect radar reflectivity image here with a radar sensor, a microwave reflectivity image here in a 6 centimeter corresponding to a 6 centimeters wavelength. Now, if you take a radar system which make an image, you will get this this noise, which is called speckle, because it uses coherent wave. All the imaging systems using coherent waves use exactly the same noise. It's called speckle. And to reduce speckle, everybody knows how to reduce speckle. Everybody knows. Everybody knows because of this. All right. When you see a painting with a lot of speckle, if you get close of the painting, you just see the speckle and you don't see anything. And if you go back, your mind and your eye reduce the speckle, reduce the noise. So when you go back, you just make a local average around the resolution cell of your eye with each bigger than the motif of the noise. So this is the most important thing to retain, the most important difference between radar and, the most important thing between radar and optic here, because I am here over, I think, a homogeneous forest. And the response I get over these pixels, over this pixel, is just due to the the distribution of the different leaves of the forest. Here, it's the same forest, it's leaves that are distributed in a different wave. I have a totally different response. Here again, and so the value of 1 pixel in radar doesn't mean anything. By contrast to optical data, the value of 1 pixel in the visible domain, you know, it's a real reflectance you get from this pixel. Here, it does not anything. It is not meaningful at all. So, what is meaningful is this just to segment, to recognize the homogeneous area, for example, here. And over this area, you just make what you do when you have a painting with noise. You just make an average over the whole homogeneous area. When you don't know the homogeneous area, you just slide a window and of a certain number of line and columns, 13 by 13, for example, and you will get the resulting pixel will be the average over all this window, and it will be. And so, when you do this, you will reduce a lot the noise. I can do it. I will. I don't tell. So just remain this, one individual value of pixel doesn't mean anything in radar by contrast to optic. So just what we do, what we want is to decrease the standard deviation, reduce the noise by making a local average. And this will reduce the noise without changing the average, because the average intensity corresponds to the radar cross-section. So you will see this is done in the practical. If you follow the roadmap, you will see, of course, when the most you average, the biggest the local window you take, if you take 21 by 21 image window, you will reduce a lot the noise, but also you will reduce a lot the spatial resolution. And so this is the deal in signal processing. You cannot have spatial resolution and radiometric resolution. One is on the contrary of the other one. Either you take benefit of the spatial resolution and you have a low radiometric resolution, or you take advantage of the radiometric resolution, but you will have a very low spatial resolution. So just here one thing. So in order to make, for example, a classification and to use radar data like optical data, you need to apply a filtering to filter the speckle, because any classification algorithm can do something with the speckle, even with GRD products. And so in that case, what you do is, for example, here, this is an image, and this is when I apply an average over a 9x9 window. You see that you have much less noise, but of course you have lost the spatial resolution. And this image is not so comfortable for our eye, but is necessary for classification algorithm. So it is the reason why you need to apply a speckle filtering to the data you have made here. You need to apply a speckle filtering to reduce, and the best filtering of the speckle is to make average of the pixels, either in the spatial domain or in the temporal domain. For example, when I go here, with Sentinel-1, you have a lot of data acquired at different time. With our processing, they are all overlapped, and you can make a temporal average. So, for example, you have 4 dates. At the end, you have just one average. It's wonderful because you don't have reduced the spatial resolution, it's pixel a pixel, but you have lost all the temporal information. If you have just one image, you have to make the sliding this window, and so you lose spatial resolution. Here no, but you lose the temporal resolution. And it is what I was showing you here. So with the Sentinel-1, so this is a Google Earth image, and Sentinel-1 in full polarization, in full resolution, excuse me. So when you put VV in red, VH in green, and the ratio VH over VV of the two polarization for the last in blue, you have this image in color, and you see you have speckle. So these are crop field. This is temperate forest, and this is some water surfaces. When you make a temporal average over 1 year, you get this one. So this is incredible. To get some radar data like this without any speckle, it's incredible. We see everything. We can have textural information we didn't get before. So, of course, if you do this, I made the average over 1 year of acquisition, about 60 different acquisitions. I have lost all my temporal information, but I still have interesting information. So just to finish, I know I'm sorry to you. So here you see how to reduce the speckle, either in the spatial domain or in temporal domain. And of course, here you get just the temporal average. You have lost all the temporal information, but you have a special filter, which is the spatio-temporal. It's average in both domain, in the spatial one and temporal one, without destroying too much information. So, for example, if you have just one acquisition here, you will make a sliding window of a 13 by 13 image. 13 by 13 size of window. Here you will take 7 or 9 by 9 window, and you will decrease less, and you will keep still, because you will make average, a weighted average. So you will keep quite temporal information, and you will have as many as date acquisition you get, but filtered. And this is what is used in the roadmap I gave you. So I have to stop because it's time. I'm sorry to be ill, because if I have been present, I think we would have go further. But really, I encourage you to make the roadmap. Don't hesitate to ask me all the questions you want, and I will answer you with pleasure. And if you have some questions now before we stop. Hello? No questions?
So first of all, thank you for doing this, even though you were ill. We really appreciate it, and we wish you a speedy recovery. And my question is, can you hear?
Yes, and me.
Okay. Anyway, my question is, how do you? I'm taking us back a bit. How do you compare images from different runs, from different relative orbits, over the same area? Because there are different angles. So how do you, for example, if you want to use it as extra to augment the data that you have for some task, how do you compare them?
Yeah. You are in the core of the problem. Yes, it's over one orbit, your area of interest can be at 30 degrees of incidence angle. Over the other orbit at 45 degrees of incidence angle. And so this is complicated because you need to know the difference. Up to now, what we do, we separate the orbits, and we process orbits separately and see what happens if what we see with one orbit is the same than the other one. But these are really new problems that has arrived with Sentinel-1 acquisitions.
Okay. And another one, if I may add, from your experience in exploring Sentinel-1 data, especially, what's your approach to visualizing information? Because visualizing information is very key to trying to understand what's happening with the different polarizations and everything. So
the best is the temporal average. What I showed you here, it's incredible to look at. You can't imagine all the things you see with the temporal averaging. Yes, with the temporal averaging of you just make the temporal average over 1 year of acquisition. So you have one temporal average for each year of acquisition. You can't imagine all you have as information about the discrimination of the radar over your study area.
Exactly.
But after, don't use only the temporal average. Is the best thing for me, for our eye, to understand what the radar sees.
Okay.
Then you have to process all the data, not only the temporal average. You have to filter the speckle over all the acquisitions and you have to run and to use the temporal information that you have in all the information. It is the reason why we use this in the roadmap I gave you. For example, for the classification, we don't use the temporal average, but we use all the different acquisitions that have been filtered of the speckle.
Ok. Ok. Merci et bonne récupération.
Oh, merci, c'est gentil. Merci beaucoup. Hein. Does anybody have other questions?
Doesn't seem so.
Still alive?
Is this working? I don't think there are other questions, Pierre.
All right. So just don't hesitate to take radar data and to play with it, because you have a lot of people who are afraid of it and they just use optical data. But now you don't. You have to use radar data with Sentinel-1 mission. There are so many information in radar data. You have to use them, and I hope I gave you some keys to use them just the beginning, but I hope at the end of the week you will be able to process everything and to use it without fears. So if there are no additional questions, comments?
Hi. Hi, can you hear me?
Yes.
Just a very practical question. You have given us the installation package for QGIS.
Yes.
My question is, if I have QGIS already installed on my machine, can I just use some plugin, or I need to?
No, because you have our customized version has to know all the environments. For example, we use Orfeo Toolbox, but QGIS has to know where is Orfeo Toolbox. We use some Python library that QGIS has to know where it is. So the best thing in that case, install our QGIS version. It can be run in parallel of your QGIS version. That's no problem.
Okay, great. Thank you.
So. Oh, Amalia, you spoke about some code I didn't give.
Yes, but didn't you solve this in the chat? Didn't you share it with the? Did he share?
I think he shared only the different kind of version of the roadmap. I mean,
Oh, okay.
roadmaps.
Yes, could you show me in the roadmap which part was? Did you notice?
Yeah, so I can also.
Oh yeah, of course.
So the part was when we do the temporal speckle filtering, and then you have to open in QGIS the model, first model, and that file under the code folder, it's not there. So the QGIS.
I give it to you now. All right. I give it to you in the chat.
So in the chat there are only 2 versions of roadmap.
Yes, there is one version for Snap, and you are speaking about the other one, I think.
So which one do we have to follow then?
This one. Oh, both do the same.
So basically now we have version when we do all the processing with the Quantum.js.
Yes, and the other one you use Snap first, and then you do it. You continue with QGIS, because the classification I do it with Orfeo Toolbox, which is a wonderful software open source, especially dedicated for this type of things. And it's really robust and works everywhere, so I use it.
Sorry. The name of the tool, Orfeo Toolbox?
Yes. Wait a minute. Wait a minute. Model this. I send you the model, and then what was the what did we say, Amalia?
Me? Somebody was asking the name of Orfeo Toolbox, so I just
Yes.
repeated that.
It is written on the and you have a.
I think now it's okay.
Okay. Otherwise,
as
drop
far
us
as,
an email.
Yeah, because then it's only the ERTs and what's.
I put the link in the chat.
Pierre-Louis, could you put your email as well if you're happy? Because I'm
Yes.
not sure they have it.
And of course, I will send you. All my slides.
Yes, yes. Yes.
I will send you Amalia, and you will send them later.
Yes, yes.
Right, super. And so in the chat, there is my email address, and you have also it on the slides I will send you.
Yes. So the PDF will be published on the website later on, not the data sets, because they are very heavy, so make sure to keep a copy.
All right.
And that's it. Can we close it? It's finished? Yes. If you like, I suppose you can close the thing. Yeah. I think there are no more questions.
So, Pierre-Louis, I think we are closing the session now, unless there is any final question from the audience. If not, thanks a lot for being able to give this lecture despite your health issues with COVID.
No.
We hope it was not too tiring for you.
No.
And,
it was a pleasure. Thank you.
We really appreciate that just 2 days after getting sick, you still accepted to give this lecture. Of course, it would be nicer to see you, but this was really the best that was possible to do. And thanks God, this lecture didn't need to be cancelled. It's one of the most important, of course, being the introduction to radar and optical remote sensing, especially radar. So it was very useful and very important that you accepted to do it all the same. Thanks a lot. Maybe we can clap for Pierre-Louis.
Thank you, Francesco, and see you next time, I hope.
Yes, I hope to. Okay, take care. Bye-bye.
Ciao.
Ciao.